So in the last video, we defined the arithmetic hierarchy again. We defined a second thing that we decided to call the arithmetic hierarchy that had the same diagram, but had nothing to do with computability, and instead had to do with this concept of definability of a set. But we have, we have defined the arithmetic hierarchy before already. It was a hierarchy of problems, a hierarchy of decision problems. And so, for our convenience, I have copied and pasted when we did that over here. So what I would like to do now is revisit that and then figure out what the hell the connection is. And this connection is going to really wire the computability stuff to the metamath stuff. This is really the connecting skeleton that that really brings it all together. In fact, it even looks like a skeleton. So we defined the hierarchy for computability in the following way. We first defined that delta 1 was equal to r. Not delta 0, by the way, delta 1. So I actually didn't have I didn't have a delta 0 before. I think I said that r was delta 0, but I was mistaken. It's delta 1. And by the way, just to remind you, it's been a while. R here, this is the set of computable problems. And then we said that sigma 1 was the computably enumerable problem. So remember that this was the computably enumerable problems. And then we defined co-re to be kind of the set of all complements to computably enumerable problems. So that was pi 1. Essentially, remember that the computably enumerable problems, we found this equivalence in which a problem is computably enumerable if you can solve it up to like an unbounded search. And then co-re, kind of the complement of that, is that a problem is co-re if it's computable up to like an exhaustive sequence of infinitely many checks. So re kind of corresponds to unbounded searching, co-re corresponds to unbounded checking. Whereas R doesn't have unbounded anything. R is sort of at the bottom, right? The searching, the thing that you're doing for each thing that you're searching through is computable. It is an R thing. Same thing with co-re. The thing you're checking is the checks themselves are an R thing. So, and then we defined sigma 2. We said that a language, remember we were calling those things languages, problems, languages, they're the same now. We said that a language is in sigma 2 if there's a computable problem J such that you're in the language if and only if, and then you could put two quantifiers here, right? And so what I'm really saying here is that a language is a sigma 2 if and only if it's computable up to an infinite sequence of checks, each of which requires an exhaustive sequence of, a search over an infinite set. Each thing that you're searching through requires infinitely many checks. It's computable up to that. It's computable up to like an unbounded while loop, and where each thing in the while loop is an infinite for loop, is basically what it means to be in here. In fact, in other words, but the important thing is not so much that, but that we are kind of 2 degrees of separation away from computable. And so the arithmetic hierarchy in this context, remember, kind of corresponded to degrees of difficulty of computability, where easy computations are the computable ones. So how far away you are from R in terms of like the number that you have here is sort of how many degrees of separation you are from something that is conceivably computable. So, and we could keep going, right? We said that a language was pi 3 if and only if for all you have 3 alternations. And you can see this looks very, very similar. For all y1 there exists a y2 such that for all y3 something computable. It doesn't really matter what's in here, right? We should just say something computable, and then that defined messily the arithmetic hierarchy. And there was no delta 0 back when we were doing this. And I could talk about delta 0, but it's really not necessary for the incompleteness theorem. Maybe I'll just write it down for your own Google searches. This is the primitive recursive languages, whereas these are the recursive languages, the actual ones. So I'll leave that to your own Google searching if you're interested in the difference between those two things. Maybe I'll make a video on it at some point. But yeah. So let's compare and contrast. So these and the comparing is a lot more important, is a lot easier to do than the contrasting because they're basically the same already, as you can see. They're basically defined in the same way. Here's the computability version. Here's two examples. Here's the sigma 2 example, just comparing the two. We said that a problem is sigma 2 if essentially there exists a y1 such that for all y2, something computable involving x, y1, and y2. Right? And this determines membership in the set L. So this is the part where decision problems and their multi-versatility, their multi-representability, as you know, not just sets of strings, but also as sets of numbers. Since we can view languages as sets of numbers, we can kind of compare these as in like exactness. We are now going to think about languages as sets of numbers and sets of numbers as languages. So start to do that for now. For our purposes now, when I give you a set of numbers, I've given you a decision problem. So let's just think of it like that. So as a decision problem, essentially you are in the decision problem if, you know, there exists a y1 such that for all y2, something computable. And whereas the definable sets version, we said you're in sigma 2 if and only if you're in the set if and only if there exists a y1 such that for all y2, something delta 0. So the only thing that's changed is the thing that's in the brackets here. We've replaced something computable involving the stuff that I'm quantifying over with something delta 0 involving the stuff that I'm quantifying over. That's it. That's all that's changed. And remember, like, we are talking about the same stuff. A decision problem is a set of natural numbers. It is. And so I can actually talk about whether or not these are the same class, exactly the same class. So this is where things are going to get, I think, kind of crazy. So here's the thing about delta 0 formulas. You can compute them on paper. So that requires a little bit of explanation. What do I mean by you can compute them on paper? So here's a formula, right? Here's a delta 0 formula. There exists a x less than 20 such that 3 times x is greater than y. So, you know, I've told you that this defines a set. And I've told you that you can think about sets of natural numbers that are defined by stuff like this as decision problems. But now I kind of want to set it up a little bit differently. Instead of thinking about this as a set, let's think about this directly as a decision problem. What's the decision to be made? The decision is whether or not this is true, right? I'm asking you, is there an x less than 20 such that 3x is greater than y? And your job is to answer that, right? That determines membership in the set. So how would I do that? You can do that on paper, right? This is a thing you can finitely do on paper. Phi of y is, so how would I do it? I give you a y. How do you compute it? Well, for each x less than 20, you compute 3 times x, and you compare it to y, and you see if it's bigger. And if you find one that's bigger, you stop and you say yes. And if you don't, you say reject. That's it. That's it. This is just arithmetic. But the important thing is I can decide whether or not I am in a delta 0 set on paper. It's just arithmetic. It literally is arithmetic. I am talking about doing arithmetic on paper. And you're starting to see how the metamathematics and the computability are just kind of flowing into each other, because I'm talking about the natural numbers. I'm talking about arithmetic. I'm talking about something that you've been doing your whole life on paper. And so by the Church-Turing thesis, we can at least immediately say that delta 0, this class that I defined in the previous video, is a subset of R, is a subset of the set of all computable problems. Because if you have a delta 0 formula, then you can compute it on paper, and so it's computable, and so it's in R. Likewise, here's a sigma 1 formula. Phi of yz equals the statement, there exists an x such that x squared plus y squared plus z squared equals 1. I used this formula in a couple videos ago. This is my example of kind of a mixed thing where you have one free variable, or one bound variable and 2 free variables. And so the question basically is, given a number, given a y and a z, is this true? Yes or no? Here's an algorithm for doing that. Likewise, if I give you a y and a z, is this true? Now, this one, I can't necessarily compute this on paper, but I can do a process where if the answer is yes, then I will arrive at a yes. And so here's the idea. If I'm given a y and a z, I can just compute x squared plus y squared plus z squared for each x, one at a time, and stop if we ever find one such that you get a 1 here. And if there is such a number, if there does exist an x, then this computation on paper will eventually stop. Otherwise, it will go on forever. And so again, that is the definition of recursively enumerable. That's the definition of computably enumerable, remember? And so by the Church-Turing thesis, we can immediately say that sigma 1, this class of definable sets, is a subset of the computably enumerable problems. Right? I'm assuming this is a little mystifying to people. We've been kind of juggling so many different versions of the same object that it's probably getting a little weird. So let me just make sure that it's very clear what I actually mean by this. What I mean by this is that this is the class of sets definable by sigma 1 formulas. If I'm interpreting that set as a decision problem, then my goal is to determine membership in it. And I can determine membership in it by simply deciding if this formula is true or not given an assignment to the free variables. And that thing to do is a computably enumerable process. And I just described an explicit algorithm for doing it on paper. And so by the Church-Turing thesis, I can do it on paper. So there's a Turing machine that accepts the language, accepts that set as a language, as a decision problem. And so I have shown then that the sets definable by sigma 1 formulas are always, as decision problems, computably enumerable. And so this is a subset of this. That's pretty crazy. That's pretty crazy. So the Church-Turing thesis has not proven it for us, but what I'm moving towards, what I'm getting at, is the following theorem, which is the crucial kind of result that is the final nail in the coffin to some extent of what we're going for. This theorem right here, which is that really what this theorem says is that the two arithmetic hierarchies are equivalent, but the really important part of it is this right here. Specifically, the result should pertain to Re. It's really the claim that the natural numbers version of sigma 1 is equal to Re, which is the same, of course, as the computability version of Re. If that's the case, then of course it's the case that it follows that the entire arithmetic hierarchy is the same, because of course then you also have that co-Re is equal to pi 1, and then remember that R is equal to co-Re intersect Re, but if you have this already, then that's equal to sigma 1, the natural numbers version, intersect pi 1, the natural numbers version, and that's equal to delta 1. So once you have this, you've actually proven it all. You can prove that the entire two arithmetic hierarchies are the same just by showing that the definability version of sigma 1 is the computability version of sigma 1. Once you've shown that, you've shown it all. So how do we show that then? Well, we want to show that the sigma 1 is equal to Re. We already have one direction of it. So in order to show that two sets are the same, in order to show that like A equals B is to, if in order to show that A equals B, where A and B are sets, you need to show, NTS means you need to show that A is a subset of B. In other words, everything that's A in A is in B, and B is a subset of A. Everything in B is in A. Now we already have one of these. The Church-Turing thesis has given us the direction that says that sigma 1 is a subset of Re. We have that. That's what we showed earlier. The other direction is going to be a little harder to do given what we've said so far, and it's a little more technical, and that's why I'm not going to go over it, but I will kind of explain what you would do, and I think explaining what you would do is probably enough for people. So essentially what we have is, given a computably enumerable decision problem, let's remember what that is. A decision problem is computably enumerable if there exists a Turing machine that essentially will, if you're in the set, then the Turing machine will eventually halt, and if you're not in the set, then the Turing machine will never halt. And so what we need to do is we need to basically come up with a number theoretical formula which somehow expresses that a Turing machine will halt. And basically the way to do that is to essentially, you have to basically come up with a system for coding Turing machines as like number theoretic functions. And the natural way to do that is using the recursive functions that Kleene defined that we talked about in the history part. But we never went over those because they're a little bit technical and mysterious and weird. But basically what you would want to do is you would basically turn back to Turing's original proof in his 1936 paper where he first defined the Turing machine and showed that his Turing model was equivalent to the recursion model. And he did that by essentially coding his own machines as recursive functions. But once you've done that, Kleine's recursive functions are functions from the natural numbers to the natural numbers. And so it naturally follows, with a little bit of more work, that any computably enumerable problem can be expressed number theoretically with a sigma 1 formula by just kind of looking at that the general form of that recursive function and just staring at it and saying, oh yeah, that's already essentially a sigma 1 formula. So basically we would have to go through a long process of like essentially coding Turing machines as like number theoretic statements, and that's a lot of, it's not hard, but it's a little tedious, but it's also not as I don't know, it doesn't seem as deep when you do it. I mean, maybe it's deep actually. Coding machines as number theory formulas is kind of cool. Maybe I'll do a series of videos doing that, but it's definitely not something that I can show to somebody that doesn't have a lot of like a strong stomach for actual math. Like, you know, the whole point of these videos is to avoid doing anything super technical. That's a little too technical, so I think people will probably be satisfied with that outline. In order to show this other direction, you'd have to basically code Turing machines as number theory statements, which can be done. And I'm just going to kind of have to leave it at that it can be done. But we have this theorem. The two definitions of the arithmetic hierarchy are equivalent. They are the same arithmetic hierarchy. I have defined the same very complicated hierarchy, admittedly, twice. And I have established now a firm connection between the meta-mathematics that we've been doing and the computability that we were doing before that. We now have the necessary connections to talk about and show immediately, very quickly, the incompleteness theorem. But before I do that, let me conclude the video with a consequence. And really, the consequence is the use of this theorem. So, note. So one thing we didn't say, for sure, is I defined this hierarchy, right? But what I didn't show you is that this hierarchy is actually a hierarchy. Who's to say that delta 1 isn't equal to sigma 1? So let me put it this way. Who's to say that these two classes aren't actually the same? And the answer is us. We've proven it already. We've proven it already. Why? We've proven it by showing the existence of the halting problem. Because the halting problem is in re, but it is not in R. Recall that the halting problem is in re, but not in R. Thus, if I view the halting problem as a set of numbers, then I have a set that is definable as a sigma 1 formula, but not definable as a delta 1 formula. And so delta 1 is not equal to sigma 1. And so that is really what's going to cause the entire house of cards to collapse. The fact that this is not true. And we're now in the home stretch. This is now the end game. So the next thing we have to do is we need to talk about axioms and proofs, and that'll be, I think, pretty fun. And then we'll have talked about all of the necessary prerequisites, and we will see that we're basically done. It'll all fall apart very fast. Maybe fall into place would be the better way to put it. So if you made it this far, I want to congratulate you for, understanding this crazy thing. Good job with that. I think the rest will be easier. So we're in the home stretch now.